All right, so this is lecture one of quantum field theory 2. And we'll start by review of what was in QFT1, what we discussed in QFT1. We talked about quantum mechanics and relativity, and then we saw that putting these two together requires that we allow for pair production. If you have enough energy, you will have to produce particles, particle antiparticles, and this means that quantum theory that puts quantum mechanics and relativity together has to be essentially many-body. It will have to include all particles at once. And then we said that there are many, you could try to cook up a many-particle theory in the language of a Fock space, or you could describe field theory. We saw that the field theory has advantages, and at some fundamental level, it's at some level it's more fundamental. It's first intrinsically many-body. It allows for pair creation. It explains antiparticles. We saw that the strong coupling, there might be no particles, and this is related to problem of strong coupling in quantum field theory. If there are any questions at any point, just ask. There will be, roughly speaking, two parts to this course. There will be the part that's about perturbative methods. This involves, we'll go over a discussion of renormalization group flow systematically. This will be the first part of the course. We'll talk about quantization of non-abelian gauge theories. And as we do that, I will review what a gauge theory is. I'll review the quantization of QED as the simplest example that we discussed in QFT1. And then we'll talk about symmetry breaking, spontaneous symmetry breaking. Then, depending on how much time we'll have, we'll discuss. Oh, actually, sorry, I forgot to include this. I will go over. That's at the moment the plan is to go over standard model of particle physics, because at Purdue we do not have a course for standard model. So I try to teach standard model right at this point. So we'll have 3 or 4 lectures. In the past, we've had 3 or 4. Last year, we had 3 lectures or 4 lectures on standard model. Depending on how the course goes and how you got where your interest lies, we could drop those lectures and focus more on non-perturbative methods, depending on how what your interests are. So we could adjust the course as we go. The non-perturbative methods, there will be discussion of, depending on, again, how much time we have, there will be discussion of anomalies. Probably this is where we're going to spend most of our time here on. Maybe briefly we'll mention extended field configuration, operator product expansion, and perhaps large N. The experience from last year taught me that we'll not have much time for these extended field configuration, large N or P. I think last time we had 1 lectures on each, or maybe we had 2 lectures on OP. I don't recall. All right, any questions? Good. So we started quantum field theory 1 by discussing what is the foundation of, what are the principles of field theory. We talked about locality, and here I want to put next to it causality. At the classical level, locality in time was tied to causality was tied to locality in time. However, quantum mechanically, this is richer. So we talked about symmetry, we talked about renormalization, even though we did not discuss renormalization or separation of scales in much detail. We touched upon various aspects of it. And the reason for that is that to understand or discuss renormalization properly, you have to talk about quantum fluctuations, or in the language of Feynman diagrams, loops. That is the first place in QFT1 where renormalization came up. And the renormalization came up over there in the following sense. We saw that any quantum field theory is needs a cutoff scale to be defined. So there is a mass scale that is the cutoff scale. It's a UV scale, ultraviolet scale. And the principle of renormalization or separation of scale is the idea or the desired property that the low energy data, the low energy physics of quantum field theory is independent of this cutoff, right? So there is a physics that we're interested in at some scale mu, say, and then there's a cutoff scale lambda. If you separate mu and lambda by a lot, the physics of scale mu will be independent of the cutoff scale lambda. This is the principle of normalization. And now hopefully it's clear for you guys that, or at least I didn't know QFT1, the reason that we could not start discussing renormalization QFT1 right away was that it really comes up when you talk about quantum fluctuations. So to see that, you have to talk about loop intervals. We're going to do a proper job of this semester. One comment is that in QFT1, we talked about classical statistical field theory. These are finite, these are path integrals that we, or field theories that we construct to study classical finite temperature physics. Such theories also follow the principle of renormalization or separation of scale, and or have to follow that rule. And the idea here is that quantum fluctuations are replaced by thermal fluctuations. And once again, there is a similar structure that there will be loop integrals and Feynman diagrams for statistical field theory, and same story goes along. All right. There's the issue of, there's also the principle of spectrum condition or positivity of energy, but I doubt that we'll have much time to spend on this. This is a more nuanced or complex issue for a more advanced course on quantum field theory. All right, any questions? There are various approaches to quantum field theory. In this course, we focus on Lagrangian formulation, but just so that you know, we discussed this very briefly last time as well. Other approaches to have in mind are constructive field theory. This is the story of Weitman axioms. This is another way of approaching quantum field theory. There is the approach of algebraic quantum field theory. This is the discussion of representation of observable algebras. We discussed this a little bit last semester. There's the operator product algebra, which is the approach that we use mostly for conformal field theories, scale invariant field theories, however, could be used for quantum field theory as well. And then the geometric approach, which is most commonly used for topological quantum field theories. But as I said, this course, for the most part, is concerned with Lagrangian formulation. All right. Before, if there are there any questions? The rest of the lecture is going to be about the first part of renormalization. We're going to talk about renormalization by discussion of dimension counting. But before I jump into that, are there any questions about the organization of the course, or any suggestions or thoughts on what topics to cover and what not to cover?
For geometric approaches, are there approaches besides topological quantum field theory that are geometric in nature?
All right, let me turn your, I have a hard time hearing you. Let me see, just 1 second. I don't know why. Can you ask your question again?
Yeah, for geometrical approach, are there examples besides topological quantum field theory that are considered geometric?
Not really. Well, I don't know. Let me start by claiming ignorance. I do not understand it properly to answer that clearly. But I can tell you that the topological quantum field theories are often discussed in the geometric, using their geometric approach. I'm under the impression that the approach is bigger, but yeah. Any other questions?
So when we talk about renormalization, something that's really important is about scale invariance. But will conformal invariance also be relevant for us here, or no?
Okay, so I think we discussed this in QFT1. Let me remind you something about QFT1. If we didn't discuss it, I guess now I'm saying it. So if you have not a non-relativistic system, you could have scale invariance, but not conformal symmetry. If you have a relativistic invariance and you want scale invariance, you are more or less forced to have the full conformal symmetry. So we didn't. I don't recall how much of it we discussed or not, but this is an important issue in quantum field theory. Can you have scale invariant relativistic theories that are not conformal? At the level of this course, the answer for you guys is no. Once you have scale invariant and relativity, you get full conformal invariance. There are some subtleties and nuances to this, and this is a topic of research. Good? Okay. But I think when we're discussing classically when we're discussing conserved charges and stress tensor, we had an argument for this, if I recall correctly. You have to go back to QFT1 lectures. All right, any other questions? Actually, well, we'll do think about standard model, and next week we're gonna have a vote whether you guys want to have standard model or not, and how much of it you want to see. All right, let's get started. Let me ask one last time. Are there any questions? All right, if not, let's get started. So this is the first lecture on renormalization, and I'm gonna start somewhere where we ended in last semester. In quantum electrodynamics, we discussed 3 loop diagrams, right? So we had the renormalization of the fermion propagator. This was the fermion self-energy. We had the vacuum polarization. This was the renormalization of the photon. And then we had the vertex corrections. These were the 3 one-loop diagrams that we discussed very briefly at the end of QFT1. And then we made a claim. The claim was this: these are the only divergent diagrams we have to deal with. How do we know that? So today we're gonna try to build an idea called dimension counting that explains or tries to explain this. There are some subtleties that come with it, and we're gonna try to explain that. Okay, so this is going to be the first step towards understanding the systematics of renormalization. All right, consider QED. So what are the Feynman diagrams like? You have the fermion propagator, you have the photon propagator, and then you have the vertex, right? So this is all you have. This is QED, right? So take any QED diagram. Call NE the number of external electron lines, legs, N gamma, the number of external photon lines. PE is the number of electron propagators, P gamma, number of photon propagators, V, the number of vertices, and L, the number of loops. Okay? Now, if you recall in our loop integrals or according to the laws of Feynman diagrams, the integrals come about every time you have loops. And in the loop, well, when you have an electron propagator, the electron propagator gives you a negative power of k, 1 over k, right? Why is that? Because the propagator for a fermion is the inverse of P slash minus M, right? Is P slash K slash minus M, and that's 1 power of K down. For a photon, it's 1 over K squared because photon is spin 1, right? And every time you have a loop integral in 4 dimensions, you have to integrate over this 4 momentum, which gives you 4 powers of K, right? So naively, just by some naive dimension counting, to every diagram, you could associate a superficial degree of divergence. This is the power of K in the numerators minus the power of K in the denominators. Power of K in the numerator come from the loops. So it's basically 4 times the number of loops, because every loop contributes as K4 to the power 4. If you're in D space-time dimensions, this would be DL. Then the number of powers of K in the denominator, because every electron contributes 1 power in the denominator, is so you have minus PE, and every photon contributes minus 2, power of minus 2. You have to subtract this. So this is a superficial degree of divergence that you could associate to every diagram. It is, we're going to see, it's a good starting point for organizing Feynman diagrams. However, it's sometimes could be misleading. Okay, so that's the basic idea. Is the idea clear? Is the idea of superficial degree of divergence clear? Okay. Now, these integrals are like this, right? So, oh, sorry. So here's your integrals that have to do with the loop integrals, right? And then you have 1 over, say, K prime 1 to K prime, what was it, PE, and then K double prime 1 to K double prime P gamma squared, right? So, and then there are integrals over these guys as well. So when you look at the divergence structure of this, when the superficial degree of divergence is what you obtain is the superficial degree of divergence comes up as here, right? So if lambda is some UV cutoff, these integrals diverge like lambda to the power of D. When D is positive, when D is 0, what you have is something like this. When D is 0, you have, for example, dk over k, right? So it's log divergent. And when it's D is less than 0, it's fine. This is the expectation based on just dimension counting. Good. Now, here is an interesting fact. Those of you guys who know topology would perhaps recognize this right away. But Feynman diagrams, by the virtue of the form, satisfy an equation that relates these. So these parameters are not independent. The number of loops in a diagram is equal in these Feynman diagram QED is equal to the PE plus the number of propagated photon propagators plus the number of electron propagators minus the number of vertices plus 1. So I challenge you guys to prove this. It's a fact about the topology of Feynman diagrams. And roughly speaking, the things to keep in mind is that these are new momentum variables we have to integrate over, and each vertex comes with a Dirac delta function. In QED, every vertex comes with 2 p electron and 1 p photon. Every internal vertex, every vertex that's in the middle, right? So try to argue for yourself that this relation holds. You could first test it by drawing a bunch of diagrams, but there's a topological reason for this. Questions? There's another relation that you could find between V and P and N. Because each propagator ends on two vertices, whether it's an electron propagator or it's a photon propagator, and each external line ends on one vertex, we can write down V as 2p gamma plus n gamma, or equivalently, we could write this half 2p electron plus n electron. These are also another set of relations that we have. So far, these two relations we found are true for all these QED Feynman diagrams. It's just because of the fact that these initial variables we start with are not independent. Using these two relations, it's a simple exercise to write down the superficial degree of divergence in the following two forms. So there's one, let me show you how it works. So 4L minus P gamma. First thing is you could do is you could write down L in this language. Using this, you obtain something that's independent of L. So you eliminate the number of loops. Then, next, you can eliminate the number of vertices by plugging this relation or this relation. And you find that what you end up with, interestingly, will end up depending only on the number of external legs. We're going to see in a bit that this is specific to QED in 4 dimensions. So some interesting cancellation happened. But this is just a simple exercise to plug them in. So why is this formula nice? Because if you want to classify the Feynman diagrams in terms of their superficial degree of divergence, you can just view them in terms of their external legs. So if you have a bunch of external legs like this, no matter what goes on inside the Feynman diagram, right? What is the Feynman diagram that contributes to this process? They will have the same degree of superficial degree of divergence, right? This is specific to QED in D equal, and sorry, I don't remember what it was. What is it called? D, space-time dimension or space dimension in the QFT1. But here I'm talking about space-time dimensions. In 3+1 dimensions, QED has this property. Good. All right. So now that we know this about QED, let's organize the QED diagrams with positive superficial degree of divergence, because those are the ones that at least superficially seem to diverge, right? And if we could, well, all we care about for now is just to classify what are the divergent ones and see if we could figure out how to deal with these divergent diagrams. So the simplest case, remember the formula is this. So the simplest case, so as you increase the number of external legs, the superficial degree of divergence goes down because n gamma and ne are positive numbers. So the worst case scenario is a 0-point function. A 0-point function will have superficial degree of divergence 4. Such diagrams are things like this, and they're called vacuum bubbles. They have no external legs. They are irrelevant to scattering. Why?
Because they have no, I mean, you can't couple them to inner states and outgoing states?
Yeah, because they have no outgoing and incoming states. Now, what do they contribute to? If you recall, when we wrote down correlation functions or the scattering matrix or amplitudes, there were a bunch of there was a way to we wrote down the vacuum of the interacting theory in terms of the vacuum of the free theory. In that perturbative expansion, diagrams like this contributed. But when you deal with some expression that is purely in the interacting theory, or such as scattering matrix, then vacuum bubbles are irrelevant. Next is the 1-point function. For example, a 1 photon coming in, or 1 electron coming in. This has superficial degree of divergence. Let me just write it down again here. So, oops. D is 4 minus n gamma minus 3/2 an electron. So, and the 1-point function, here D is 3 and here D is 5/2. Both of these vanish. Do you know why?
Wick's theorem?
No. Well, Wick's, yes, Wick's, but no. Wick's theorem, we proved it for scalar field, right? There is a version of Wick's theorem at work, but there's which principle of quantum field theory that tells you that these will vanish? Which principle of QED? Wick's theorem was not a principle, it was something we derived. The fact that Lorentz invariance requires this to vanish, right? If you look at this correlator, what is this? This is something like this, A mu. This is not a Lorentz scalar. So Lorentz invariance will tell you that it must be 0, right? Under Lorentz transformation, this is going to be multiplied by some Lorentz matrix. The only way for it to remain invariant is that it's 0. Similarly, a fermion 1-point function is also similar. So the only way for Lorentz invariance tells you that this is 0. So the 2-point functions are the photon propagator has superficial degree of divergence 2, and the fermion has superficial degree of divergence 1. However, here is the first case of seeing that superficial degree of divergence is not always the best guide. This guy, we saw in quantum field theory 1 that we calculate the 1-loop correction to this. This was the vacuum polarization. And then we saw that it diverges like log lambda and not like lambda 2. Do you remember why? In expansion of this, there was a lambda 2 term, but that violated gauge invariance. Otherwise, another way of saying it is that it violated ward identities. So even though the superficial degree of divergence is 2, that d equal 2, the lambda squared term was not allowed. It was just an artifact of the fact that we're using unphysical degrees of freedom that are not present. So this is log lambda divergent. For the fermion, d is equal to 1, but it's still log lambda divergent. This is another, I guess, warning for why you should be careful with the superficial degree of divergence. But as a first principle, it's not a bad principle for organizing your the structure of your diagrams. Are there any questions? All right. Next, let's go to the 3-point functions. So the vertex has superficial degree of divergence 0, and it's actually indeed log lambda divergent. A 3-point function with 3 gammas coming in, this would have superficial degree of divergence 1, but this vanishes. Why? Why does this vanish? Because it will have to contribute to a 3-point function of a Lorentz scalar. So A mu, A nu, A alpha. There is no way of contracting these indices to build a scalar, Lorentz scalar, right? For the propagator of 2 photons, you contract them using A mu nu or in various ways, right? But here, the Lorentz invariance tells you that the 3-point function will have to be 0. The 4-point function has superficial degree of divergence d equals 0. But the divergent part vanishes due to the word identities. This is analogous to the 2-point function and the fact that the word identities required that the most divergent piece of the contribution to the diagram, which is lambda squared, is absent. So what I'm going through requires a little bit, you have to go through this a little bit more slowly and just consider them case by case. There are lessons to be learned here. In general, the superficial degree of divergence is only a guide. As we said, d equals 0. This diagram that has no loops, d is equals 0 for it, is finite. This diagram has d equals 0, is log lambda divergent. This diagram has d equal 2, is log lambda divergent because of word identities. This diagram has d equal minus 2, but it's log lambda divergent. This is a very, very curious case. So this tells you that the analysis that we had above is sketchy. Why? So what we saw, one phenomenon that led to the superficial degree of divergence not being an accurate representation of the divergent structure of it was that the most divergent term was somehow unphysical due to word, and was ruled out by word identities or gauge invariance. But here we're seeing a different phenomenon. We're seeing a structure where the superficial degree of divergence is negative, which means that you shouldn't have any divergences, but the diagram diverges. This is another phenomenon, and it has to do with subdiagrams that are divergent. The origin of this is subdiagrams like this, which is so there is a subdiagram to this. Part of this diagram involves a divergent thing. So there is this thing that sits inside this. And if you went through the analysis of this, you will conclude that the origin of this is this divergent subdiagram. But then there are diagrams with negative degrees of superficial degree of divergence that are actually indeed finite. So in summary, superficial degree of divergence is only a guide. We will actually use it as a guide to organize the perturbation series, and actually will take care of these cases, these, I guess, surprising cases at first in a systematic way. But before doing that, let's just generalize this discussion of the superficial degree of divergence to other space-time dimensions and other theories. But before I do that, I'm going to pause for questions, right? So what we discussed is superficial degree of divergence in QED. And we said that it's not necessarily the most accurate representation of the divergent structure of the diagram. We saw two reasons where it misrepresents it. Sometimes the most dominant term is absent due to some, because we have introduced some unphysical degree of freedom, some gauge invariance or word identities. Sometimes there are divergences in the diagram that are not visible in the superficial degree of divergence, and has that to do with subdiagrams that are divergent. In the remainder of this lecture, we're going to ignore these complexities and just talk about superficial degree of divergence in other space-time dimensions and other theories, because we're going to see some further structure that underlies the Feynman diagrams. Are there any questions? All right. Now let's just repeat this for QED in these space-time dimensions. So what happens is the number of loops is multiplied by the space-time dimensions minus PE minus 2P gamma, because no matter what the space-time dimension is, the propagator for a photon is 1 over k squared, and the propagator for an electron is 1 over k slash minus m. Okay. So now we can use the two relations we used in the past, right? These two relations. We still have them. This V could be written in terms of P and N gamma and P and N electron. And also we have this rule. So if we plug them back in, what we find in the general space-time dimension is the following equation. The superficial degree of divergence is this. Now you notice something interesting. This depends on the number of vertices in addition to the number of external legs. It depends on the number of vertices. However, the coefficient of it vanishes at d equal 4. So it was a coincidence that QED in 4 space-time dimensions, the superficial degree of divergence, does not depend on the internal structure of the diagram and depends only on the number of external legs. In d less than 4 dimensions, what happens is that this is positive. So more vertices means less divergent. In d equal 4, more vertices are as divergent. In d larger than 4, more vertices are more divergent. Right? So what is the idea? The idea is that there's a whole bunch of things that come in, and then I'm gonna write it. There is a way of filling this in, right? And there are all sorts of ways of filling this in. To this amplitude, all sorts of diagrams contribute. And you could just continue drawing various diagrams that contribute to this and that include more and more vertices. In d equal 4, if you're doing QED, you could pick any one and calculate the superficial degree of divergence, and then that's the superficial degree of divergence for all of these diagrams. Because you have to add the diagrams together. What matters is the most divergent one. When d is less than 4, it just means that you draw the diagram with the lowest number of vertices, and that tells you the degree of divergence, superficial degree of divergence. With d larger than 4, it means that as you increase the number as you increase the number of vertices, the divergence gets worse and worse. So this amplitude, to calculate an amplitude like this, you have to sum all of them. So within this amplitude, there exists a Feynman diagram with a superficial degree of divergence that's arbitrarily large. The divergence is as bad as you can imagine. Is that principle clear? It's only in 4 dimensions in QED that this magical thing happens. So what does this mean? It means that we could split our analysis of QED into 3 types of, these 3 types of behavior can go with different types of names. So we say a theory is super renormalizable if then there's a finite number of Feynman diagrams that superficially diverge. This is the case in d less than 4. In QED. In QED, d less than 4, there's a finite number of Feynman diagrams that superficially diverge. I repeat, this analysis is based on naive dimension counting that, as we said, does not always capture the correct divergence structure of the diagrams. However, it could still be used for classification of theories for reasons that will become clear later. So a theory is super renormalizable if there's only a finite number of Feynman diagrams that superficially diverge. QED in dimensions less than 4 space-time dimensions is super renormalizable. The theory is renormalizable if a finite number of amplitudes superficially diverge. However, divergences occur at all orders in perturbation theory. That's the case of d equal 4 and QED. And the theory is non-renormalizable if all amplitudes are sufficiently high order in perturbation theory diverge. That is the case of QED in dimension, space-time dimension larger than 4. Are there any questions? So we use the example of QED because it has such simple, first, it's an interacting theory, but it has very simple Feynman diagrams to run our argument of dimension counting and see this structure of super-renormalizable theory, renormalizable theory, and non-renormalizable theories. Now, in the remainder of the lecture, what we're gonna say is we're gonna try to extend this a little bit further and related to, well, to sort of generalize the lessons that we learned from this example of QED and abstract out the lesson in a form that could be easily generalized to other theories, whatever they may be. So in summary, what we said is that QED in less than 4 space-time dimension is super normalizable, D equal 4 is normalizable, and D larger than 4 is normalizable. For now, we will treat non-renormalizable theories as undesirable. We'll come back to this later. There was a time in quantum field, in theoretical physics, when non-renormalizable theories were considered sick. They're considered bad and sick. That was a while ago. Things have changed. However, if you have a theory that's renormalizable, that's really, really good news because you have a lot of control over your calculations. Famously, Standard model of particle physics is renormalizable, and Nobel Prizes were given for that proof that Standard model is a renormalizable theory. It's a fact about Feynman diagrams of Standard model of particle physics. All right. Next, what we're going to do is we're going to repeat our analysis in scalar field theory. So here's the action. Half del mu phi squared minus half m squared phi squared, but with a generic phi to the power of n interaction. Okay, so do not confuse this little n with this capital N that we're going to say. And the idea is to come up with some sort of a principle that can tell you about the renormalizability or non-renormalizability or super-renormalizability of the theory by staring at the Lagrangian density. That's the idea. Good? So a theory like this, there will be Feynman diagrams that we're going to call the number of external lines capital N, because there's only one type. P is the number of propagators, and V is the number of vertices. Oh. The superficial degree of divergence is the space-time dimension times the number of loops minus 2 times P. Here we have the relation. So these are the two relations that we said before. The number of loops is related to number of propagators, lines, and vertices in this using this relation. This is reminiscent of the previous relation, the topological relation we had. And then we have this we have another relation that says n, which is this power, times v is capital N plus 2p. Prove this. Prove this and compare these two equations to the QED2 equations that we had. The first one is exactly identical. It's just a fact about Feynman diagrams. But the second one is a little bit, well, it's actually pretty simple as well. These two rules replace these two rules that we had before, right? So the two rules that we saw in the case of, there was this relation, and then there was this relation. So here it's clear that if you have only one type of particle, L is P minus V plus 1. So that's the relation that we just saw. And then the vertex relation is this. You could easily argue that you end up with, where is it? You end up with this relation. Now, plugging these two inside this equation for superficial degree of divergence, we get a formula like this. Now what happens is we have a more general formula that depends on the interaction term and the space-time dimensions, right? So here's something interesting. If this power is 4, so little n is 4, and the space-time dimension is 4, this term vanishes. Is that right? Yeah, true. Yeah, this term vanishes. So there's no dependence on V anymore. Right? And we end up with a situation like QED. If this is 4 and the space-time dimension is 3, you end up with a super normalizable theory. If D is equal to 2, this is also super normalizable. So what we see is that similar to the case of QED, the lambda phi 4 theory is renormalizable just at D equal 4. For lower dimensions, it's super normalizable, similar to QED. And above that dimension, space-time dimension 4 is actually non-renormalizable. So we see a similar structure for lambda phi 4. However, you see how it depends on the interaction term if you consider other theories. Right? Okay, so what is the lesson? What is the structure behind these Feynman diagrams? Are there any questions, actually? One of the things that you probably might suspect at this point is that there is a reason that people discuss lambda phi 4 as the first example of quantum field theory in 3+1 dimension in most textbooks, because we're interested in the simplest example of a quantum field theory that mimics the structure of QED or other theories that we deal with. These QED in 3+1 dimensions is renormalizable, so is lambda phi 4 in 4 dimensions, right? So that's the reason, underlying the reason. Not every textbook follows that. So I believe Srednicki does, if I remember correctly, 6 dimensions. No, what do they do? Well, they take another example. All right. So now, how do we relate this observation? How do we abstract this out a little bit further? How do we generalize this lesson a little bit further? Consider the action. We said that the principle of locality tells us that in QFT1, we said that the principle of locality tells you that action is an integral over Lagrangian density. This integral over space-time, action has, if we set h bar equal 1, has dimensionality 0. So Lagrangian density has dimensionality d space-time. In the case of a scalar field has Lagrangian density. The kinetic part of it is this. So the dimensionality of phi has to be d minus 2 over 2, right? That d minus 2 over 2 is here. And it's here, right? So now, if you have a lambda phi n term, the dimensionality of this has to be d as well. But the dimensionality of phi n is n times d minus 2 over 2. So the dimensionality of lambda, let's call this term, let me call this lambda n phi n, right? So then the dimensionality, because the dimensionality, no, I did this wrong. This has to be d. Yeah. then the dimensionality of phi lambda n is d minus n times d minus 2 over 2. Good? What is this? Do you recognize this term? It's minus of this. Right? Good? Is this part clear? This is a very important step. Of course, if you had another field such as with a field with different spin, the answer that this might look different, right? So for example, if you have a fermion, then the fermion, instead of having del phi squared, will have psi del psi, which will have a different dimension, right? The dimensionality of that would be d minus 1 over 2. Good? Because there's only one derivative. Now consider a diagram for this lambda phi n theory with n external legs. Right? So something like eta phi n. And this eta would be the eta would be d minus capital N d minus 2 over 2. Any amputated diagram with capital N external legs has dimension d minus n times d minus 2 over 2. Good? If this amputated diagram has a term in it that has v vertices with interaction lambda n phi n, then that term in this amplitude, that Feynman diagram that contributes to this amplitude, will scale like lambda to a power of v times capital lambda to a power of the superficial dimension. Because capital lambda to the power of superficial dimension is clear. Lambda is the thing that comes with every vertex to the power of v. Why didn't we talk about this before in the case of QED? Do you remember? Do you know why? Because this lambda in the case of QED was dimensionless. What was lambda in the case of QED? The 3-point function. What's the tree-level 3-point function? What was 3-point function in the Feynman diagram of QED? It was IE gamma mu. E is a number, gamma mu is dimensionless. The contribution of this interaction term, the contribution of the Feynman diagram with V vertices with this interaction will have this dimensionality. Right? The very fact that this diagram will have to contribute to this scattering amplitude tells you that they have to have the same dimensionality. So V times D minus N times D minus 2 over 2 plus D will have to be little d minus N d minus 2 over 2. You could rearrange this to find the following formula. What is this formula? This is this formula writes the superficial degree of divergence in terms of number of vertices and external legs for a theory with lambda phi n. Right? So we first started with QED in 4 dimensions. We saw that it's renormalizable. Then we talked about other dimensions. Then we talked about lambda phi 4 in other dimensions, and now lambda n phi n in other dimensions. We see that it's super renormalizable. This is the dimensionality of the lambda n term, right? It's super renormalizable if the coupling constant of lambda n phi n, if the coupling constant has a positive dimension. It's renormalizable if it has 0 dimension, and if it's non-renormalizable, it has negative dimensions. Right? Because if lambda has dimension 0, this term goes away. It only depends on external legs. We're in the renormalizable world. It's only the amplitude that diverges, and if a certain amplitude diverges, all the diagrams that contribute to that amplitude will have the same superficial degree of divergence. If lambda is larger than 1, sorry, this is the minus dimensionality of lambda. The lower point vertices that contribute to the amplitude are the ones that you only have to consider. As you increase more and more vertices, they become, the superficial degree of divergence goes down. So this is super normalizable theory, because the number of amplitudes that have positive superficial degree of divergence is finite, and to each such amplitude contributes a finite number of diagrams that are superficially divergent. Therefore, the theory is super normalizable for when the dimensionality of lambda is positive. When the dimensionality of lambda is negative, it's non-normalizable. That is obvious. Good. So this is what we're gonna take home as a take-home lesson. So if you have a theory, some Lagrangian density, and there is some sort of a free part to the Lagrangian density, and then there is an interaction of form lambda O. This O could be any operator. If it's a free part is scalar field, this could be phi to the power of n, right? It's a coupling that naturally sits next to these guys. And it's the dimensionality of this coupling that tells you whether this theory is normalizable, non-normalizable, super normalizable. If the dimensionality, if it has no dimension, has dimension 0, then it's renormalizable. It's the case for lambda phi 4. Lambda is dimensionless. It's the case for QED, because the coupling of QED, which is it's A mu psi gamma mu psi. The coupling of it is IE, if you wish, gamma mu, and that's also dimensionless. When this is dimensionless, the theory is normalizable. When it has negative dimensions, it's super normalizable. If it has positive dimensions, it's super normalizable, and if it has negative dimension, it's non-normalizable. Questions? All right, I'm gonna end with a summary of what we discussed. Dimension counting is a guide to systematically study the divergences in Feynman diagrams in perturbation theory. When you have an action like this for a scalar field with some coupling like this, for example, lambda phi n, is the dimensionality of lambda that decides normalizability. If lambda is positive, it's super normalizable. These theories are very, very nice and good. If lambda is equal to 0, it's renormalizable, and if its lambda is negative, it's non-renormalizable. Here is a lesson. I'm telling you in advance a little bit where we're going with this. We're going to see that when the theory is super renormalizable, perturbation theory works really, really well. We will talk about renormalization, and we'll see that renormalization will systematically get rid of all the divergences properly, and everything is well defined and nice. Such theories have a very, very nice UV behavior. If the theory is renormalizable, still the UV behavior is under control, hopefully, and it's actually a little bit more subtle, but perturbatively, we succeed at making sense of some important renormalizable theories, such as standard model of particle physics, QED, and such. Actually, QED does not make sense. We'll see that. But standard model will end up being normalizable and nice. And then there are theories that are non-normalizable. And at this point, we're not going to be able to deal with them perturbatively, but we'll perhaps at some point we'll get to exact RG. That's when we say that non-normalizable theories are not inherently wrong or bad. When a theory is non-normalizable, is an indication, it's telling you about some new particles or degrees of freedom at scale lambda that you haven't yet discovered. So non-normalizability theory is also an informative fact about the theory, that there are interactions and particles you have not observed yet, and you should expect them to appear. All right. One last thing to mention is that another important lesson, in lower space-time dimensions, QFT is less divergent, it's better behaved. In 1+1 space-time dimensions, things are particularly good for the following reason. Can actually anyone tell me why is 1+1 dimensional quantum field theory very, very nice from the point of view of renormalizability? For example, a scalar field. So actually, let me explain this a little bit better. So if you have a scalar field like this, the action is this. So what's the dimensionality of phi? The dimensionality of phi is this, which is 0. So if your view of phi includes an arbitrary polynomial in phi, like this, what's the dimensionality of lambda n? 0. Oh, no, sorry, what did I say? No, that's wrong. It will be actually better than that. So this will have to be, the dimensionality of this has to be 2, so well, it's 2. Yeah, it's 2. So the theory is super normalizable, always, for all interactions. Two plus one dimensions is a little bit better. 3+1 dimensions, you're already in the world of, in a lot of theories, you're already in the world of normalizable theories, and sometimes non-normalizable. And as we go to higher dimensions, things will get worse and worse. All right. Are there any questions? All right. If not, this is the end of this lecture. And the next lecture, we will continue our discussion of perturbative normalization by discussing Feynman diagrams in more detail. Thank you so much, guys.
Thank you, Professor.